As mentioned, my name is Petar Veličković. I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And today, I'll be talking to you about what it means to reason algorithmically, and I'll try to elaborate a bit more on my personal journey in this area. So, specifically, what I'm going to be talking to you about in today's talk, and what I kind of want you to keep in the back of your minds throughout it, is we're going to be talking about classical computation, the kinds of things you might see in a typical undergraduate computer science course. So polynomial time algorithms, data structures, and so on. So think of things like sorting, searching, pathfinding, clever ways to organize information, and so on and so forth. And of course, because this is a deep learning-oriented workshop, we'll be talking a little bit about how we can take the spirit of that computation and capture it with neural nets. Now, everybody in this room probably has their own journey that led them to this intersection between deep learning and combinatorial algorithms. For me personally, it started out from quite a young age, actually. So I've actually participated in many of these competitive programming events throughout primary school as well as high school, and even managed to win a few prizes. This is our team winning the gold medal at the Northwestern Europe Regional of the ACM-ICPC. And it's something that, you know, these kinds of things follow me to this day, apparently. You might have seen a few days ago, there's a new video out on YouTube where myself and a few of my colleagues tried to solve one of the more challenging lead code problems on a whiteboard. It's a kind of a promotional part of a new machine learning street talk episode, which will focus on a lot of the things I'll present today. So if anything today catches your interest, I do recommend checking that out as well. And now let's talk about how, you know, starting from those beginnings and, you know, going into a career in machine learning, I kind of came back and did a full circle to where I am right now. So these aspects of competitive programming, trying to write a program that satisfies certain time and memory constraints as quickly as possible, is what initially brought me to computer science. And actually, I believe many people who do machine learning nowadays have a somewhat similar story. And in 2014, at that point, I still just wanted to do algorithms and software engineering. I had no intentions of doing machine learning. I decided I'm going to do a bioinformatics project for my undergrad because I heard bioinformatics is full of algorithms. However, what happened is that my advisor immediately told me, no, you shouldn't do this algorithmic stuff. You should learn machine learning. Everybody in bioinformatics is doing machine learning right now. So yeah, that ended up with me doing an entire PhD on machine learning and graph neural networks. But I never really forgot these kinds of roots. And what I'll tell you about in this talk is how I went full circle combining algorithms with GNNs. So first, how my views about the intersection of these two fields evolved over time. And in the process, I'll introduce neural algorithmic reasoning, which is an emerging, exciting area of research that I've been involved in over the past 2 or so years. And ideally, I'll try to impart and illuminate my own perspective on how we can use some of these things to achieve generally intelligent agents, which is a pretty topical area of discussion nowadays. Now, luckily for me, Stephanie already mentioned a lot of the key details on GNNs in her talk, so I don't have to go in a lot of detail here. But I just thought it would be good for us all to be on the same page. When I say a GNN, I typically mean this class of one-hop neighborhood models that look at features of a node in a graph and its immediate neighbors, and based on this multi-set of neighbors, predicts updated embeddings for every single node. You add some nonlinearity, you stack these layers, on and on, on and on. There's many different ways in which you can implement a GNN. I have separate talks where I talk about various flavors in which you can do that. From left to right, convolutional attentional message passing, they increase in expressive power. You can see the computations taking place are more complicated as you go left to right, but they all satisfy this notion of permutation invariance to the neighborhood, so they all have this aggregator O+, which can be sum, mean, averaging, or whatever, which kind of respects the randomness of the order of the neighbors. Okay, so after I got my PhD in 2019, I joined DeepMind, and shortly after, I met a research scientist at DeepMind who's named Charles Blundell. And both of us are computer scientists by training, so we had a lot of really fun discussions at the beginning about this intersection of the two fields. And it all started, like this whole area started from us asking a very interesting but seemingly quite inconsequential question, which is, could we have neural networks that learn to execute some of these classical algorithms? Initially, we wanted it just to be a way to measure expressive power of neural networks, because there's a lot of nice properties in trying to learn to execute an algorithm. You can generate infinite amounts of data, so it's very easy to not be limited by any particular data set. They involve complex data manipulations, so learning to execute them truly measures how skillful your network is at doing these kinds of manipulations. And there's a very clearly specified generating function for your data, meaning you can do credit assignment or even explainability on what this model has learned to do. But not much else. We just really wanted to benchmark how good are different models at doing this thing. So maybe a deeper question that was kind of lurking underneath is, what makes a particular neural network better or worse at fitting certain classes of algorithmic tasks? Stephanie already talked about this in her talk, but once again, it's good to kind of give a recap on how we thought about making all of this happen. So the key concept in this area, the key theoretical concept that allows us to take a neural network architecture and talk about will it be a good or bad choice for a particular algorithmic task, is this notion of algorithmic alignment. And here you can see some 3 specific classes of neural network architectures. You have MLPs that just flatly concatenate all the inputs together and process them together without any symmetries applied. You have deep sets, which identify individual objects in the input and then process them individually, then summarize them. And you have GNNs, which also additionally support pairwise relational reasoning between these objects. And it's actually possible to mathematically formalize when a particular architecture might be better for a certain kind of task. When I say better, I mean in terms of sample complexity. So how many training examples do you need to fit that task to a certain level of error? And in this first paper from Stephanie's group, from Keo Luxu and others, you have this question of what can neural networks reason about, and there they prove a theorem that says that better algorithmic alignment leads to better generalization. So if you line up the parts of your neural network such that they line up with your target algorithm, they will fit the problem better than if you don't do that. So now this begs the question of what do GNNs algorithmically align to? And in this same paper, they show that graph neural networks algorithmically align to dynamic programming algorithms. And you can see this nicely pictorially represented here. I have a classical dynamic programming algorithm, which is Bellman-Ford, so a standard pathfinding algorithm. And you can see how the different parts of that algorithm very nicely line up with different parts of the GNN equation, right? So you can think of the distance variables that get updated as node features. You can think of the addition of distance variables with edge weights to be the messages sent across the GraphNet. And you can think of this minimization across all the neighbors as the aggregation function of the GraphNet. So there's kind of a nice way to break up the dynamic programming update rule into something that aggregates over neighboring subproblems. So in that sense, GraphNets align well with dynamic programming algorithms.
So is there a formal definition of alignment?
So I would consult the paper to see exactly how they define it. But yes, they talk about a decomposition of algorithms and networks into submodules, effectively. Yeah. And empirical results that they have pretty much validate this. So if you have some kind of summarization problem where it's just a summary property of the input set of variables, MLPs perform really terribly and deep sets and GraphNets perform well. If now you have a question that requires you not only to aggregate over the set, but also identify certain elements in the set, suddenly deep sets struggle a lot because from that summary you cannot really extract individual elements that easily anymore, but GraphNets still perform well. And on dynamic programming, GraphNets perform the best, and the closer you stack the number of layers to the number of steps that the dynamic programming algorithm needs to do, the GNN will perform even better. So what does this mean for us? Well, we already knew we wanted to use GNNs, and this result just made us more confident that we should use them. So this led us to our first paper, Neural Execution of Graph Algorithms, which we published at ICLR 2020. And basically, why did we need to make another paper on top of this finding? Basically, algorithmic alignment is a very powerful tool for deciding which model class you should use, but it doesn't allow you to be reckless with your architecture, basically. So even though GNNs might be well aligned with algorithmic tasks, you cannot just throw any GNN at a pathfinding problem or something and expect gains out of distribution. And for us, out of distribution is actually critical, because if we say you have a model that's truly learned to imitate an algorithm, it should gracefully perform no matter how big of an input I give to you, right? It doesn't matter like how big the input gets, you shouldn't completely collapse and give me useless answers, right? So not necessarily captured by the training data. And if you're not careful, if you use just any expressive GNN class, you can very easily overfit to the training distribution, meaning that you actually sidestep the algorithm itself and you hack the training data in one way or another. And in our paper, we actually make several key observations on how you can be careful with your inductive biases to make this a bit easier to do. Yes?
In the, say, alpha tensor work, there is no notion of data. Trying to learn a procedure that works for all matrices of dimensions min n by p.
Right.
And there's a nice way to abstract that search problem, right? But here, data is coming up, and then immediately you have this fundamental gap between the correctness of an algorithm, which should hold for all inputs, and something which needs to, suffer the risk of overfitting and all
yes.
that. Then what is your perspective on, these two kinds of visions? Like I see the alpha tensor type of search versus data-driven kind of search, like how you present.
Yeah, so I think it's a general kind of gap between supervised and reinforcement learning can also be mentioned in this context. And I'll talk quite a bit about perspective for these models. I would say, at least for now, don't use them if you need something absolutely correct all the time. But if you want something to give you a representational advantage informed by an algorithm, then yes, especially at large scales. And I'll talk about many examples of how we were able to do this over time. But yeah. Okay, so let's talk about some of the key insights in our paper that allowed us to do this efficiently. The first one is encode, process, decode. So the previous paper that I told you about used n GNN layers, and every one of them had unshared parameters, right? And this is fundamentally not going to work out of distribution because I can always come up with an input that makes you need to run the algorithm for more than that many steps, right? And also fundamentally, the algorithm is just some iterative procedure that repeats itself, right? So we did a completely different style of learning where you have one shared processor layer that gets iterated a certain number of times, and then you just have some encoders and decoders that map to and from your data space. So that was the first thing that we did. We replaced the stacked unshared GNN with the encode, process, decode architecture, which nowadays is quite standard both in learning algorithms and in learning simulations. So this is basically what it looks like. You have your input, say here in the case of breadth first search, your initial input might be a source node. All the other ones are tagged with something like infinity. You embed them into some space, and then your GNN then just does message passing over those latents, and that same GNN is iterated sufficiently many times, from which you can then decode the shortest path tree starting from node 0. So this is what it looks like maybe on a more abstract scene. So you have some abstractified inputs, you encode them, you run a processor for a certain number of steps in the latent space, and then you decode the outputs that you care about. Okay, now the second one, and a very important one, is that the prior work I told you about used the sum aggregation. So for them, the aggregator was the sum, right? Now, there's a lot of good reasons to use the sum aggregation. For those of you who know about GNN theory, you'll know that using the sum aggregation leads to maximally expressive GNNs over discrete features, especially with respect to the Weisfeiler-Lehmann hierarchy. However, many algorithmic tasks, including shortest paths, do not perform summations, right? They perform selections. Each node chooses a neighbor which is optimal with respect to some metric, right? And that's an optimization operation which doesn't align with sum, it aligns with max. So we did a very simple thing. We replaced the sum with a max in our GNNs. And this goes against conventional wisdom. Like these expressivity of GNNs papers typically say max is a weaker aggregation than sum because there are many inputs it cannot distinguish. However, for these kinds of problems, you don't need that kind of power. You need better alignment, right? So all we've done is we've taken that previous picture and made sure that the aggregator we're using is max. Okay? And the last one, but also very important one, is we use this concept of a stepwise supervision. So the prior work only supervised on the final outputs. So this makes, for example, all sorting algorithms equivalent to one another because the input is an array, the output is a sorted array, and I don't care how I got there. So we thought it would be a really good thing to do to get more robustness and more alignment to leverage stepwise supervision. So we don't just supervise on the last step, we instruct the GNN at every step to line up with what the algorithm is doing. So for example, if you want to do a path-finding algorithm like Bellman-Ford, after you do k hops of GNN, you supervise it to predict the shortest paths using no more than k hops away from the source, right? And these three ingredients combined together allowed us to successfully generalize to 5 times larger graphs at test time, right? For 2 path-finding problems like Bellman-Ford. And other strong baselines like transformers or sum-based GNNs could fit the validation data really well. So the same distribution as the training set, but they clearly sidestepped the algorithm because at test time they struggled while extrapolating. Some of them even exploded, like the signals exploded at test time.
So this is possible because of the embedding and decoding that you have explained before, right? I mean, you have a block that is actually repeated itself based on the tools, this embedding and decoding after, right? Coding
yes. Exactly. So that's the third ingredient we have. At every step, we take what would the actual algorithm compute after this many steps and supervise the outputs of a GNN to match that. Now, I'll mention this, that maybe it's an idea familiar to some of you if you've seen some of these older papers like neural Turing machines. Algorithmic alignment, at least at an intuitive level, is not a very new idea. Neural Turing machines and differentiable neural computers are examples of architectures that were even published in Nature many years ago, and they have many of these components that line up with what a Turing machine would do. So it's a super influential work, and actually, in their efforts to kind of make a neural version of read and write to a memory, they invented one of the earliest forms of transformer attention, right? Way before the transformer itself. However, nobody uses neural Turing machines today in practice. Why is that? Because they added so many different components at once, and it's very brittle on all the tasks that are not the tasks they looked at in their paper, right? So likely due to many components introduced at once, it's just too brittle. So our work is a bit of a paradigm shift in this regard. We're not trying to throw in 100 components at once, but we try to add one component at a time and use algorithmic alignment to verify that that component makes sense to add, right? And we can generally keep playing this game. Like, we use these three ingredients to align better with pathfinding algorithms. You can then, for example, have specialized architectures that align with n-log-n sequence algorithms. You can align with iterative reasoning algorithms. You can align with data structures. This is our own paper from NeurIPS a few years ago that looked at these things. You can also have auxiliary memory. So if you need to create additional nodes, you can build GNNs that align with that. And it seems like, you can have these fine-grained steps, and this gives you better out-of-distribution generalization than if you just throw a usual off-the-shelf state-of-the-art architecture at this problem. And eventually, the fact we saw all these insights empirically, they carried over into more fine-grained theory. So Stephanie earlier today presented their paper on linear algorithmic alignment, which showed theoretically that if you put a max aggregator in there, it will give you a better generalization performance. There's a very nice geometric argument that can be made there. Then the group of Bruno Ribeiro from Purdue generalized this even further to talk about that this is just a special case of a more causality-based argument, where if you have a causal model of what your test data will look like, you can exploit that to build better aligned models. And more recently, with Andrew Dudzik and myself, we had this NeurIPS paper that uses category theory to try to formalize algorithmic alignment in an even more kind of general abstract mathematical light. Now, this was just a whirlwind tour of how to build architectures that are better at fitting a particular algorithmic procedure. But then we're always faced with this question over here. Why not just run the algorithm, right? So based on all of this insights in these various papers, we might now have a decent grasp on how to build networks that can fit an existing target algorithm. But then you send it to a conference and you get reviews like this, right? What's the purpose of learning to execute an algorithm? Why not just run the algorithm itself? And my personal favorite, this paper will certainly accelerate research in building algorithmic models, and there's certainly a lot of researchers that would make advantage of it. I'm just not sure this research should even exist, right? This was a very wonderful review to receive as an author of a paper, right? Now, there's a lot of good reason why people might want to say that, like But tautologically, the target algorithm itself will always execute itself better or equally good than any GNN you'd learn over it. So up until this point, we had a curiosity-driven work where we just wanted to see, could a GNN learn to do this? But now it was time for us to see, can we actually make it useful? Right? We came up with many ideas over the past years. Some I even presented at a previous IPAM workshop a few years ago. But today I'll present to you the three that, in my opinion, saw the most impact over the years. So first, algorithmically aligned models can accelerate science. You might have seen this paper, so if anybody ever needs any evidence why algorithmically aligned models are a valuable thing to do and why the research should exist, they should just look on the cover of Nature, right? So this was a paper that we published in December 2021, which was released on the cover of Nature, where we used neural networks to help mathematicians find the hidden structure inside mathematical objects. And then mathematicians used the insights from those models to prove in two very distinct areas of mathematics very impactful conjectures that have been published in top-tier mathematical journals. And actually, I think 2 weeks ago at IPAM, there was a workshop in AI for mathematical methods where several of our co-authors presented these works as well in more depth. So you might have heard about this. But honestly, I find cover of Nature to be less consequential. I find more interesting what the independent mathematical reviewers said on this particular paper. And basically, people whose objective is to find as many, points for us to improve on our paper genuinely said things like this, where this is a new phase of using machines for mathematical research. They cannot imagine a mathematician not using these methods if they were available. And they judged the individual contributions, the 2 mathematical contributions we had, as worthy of top-tier mathematical journals. And indeed, since then, we have been able to publish one of them in a top-tier mathematical journal, Representation Theory. You can see it was a long-standing dream of mine to be a co-author on a mathematical paper. I'm happy that I've been able to make it happen, even though I don't really understand any of the mathematics. So I don't have a lot of time to talk about this work, but I'll just say the essence of how it relates to algorithmic alignment. So in this work, we train a GNN to fit some mathematical data set that the mathematician cares about, and then we use some simple saliency methods, like gradient saliency, to tell the mathematician which parts of these complicated inputs are most important, most interesting to look at. Then the mathematician can go away, stare at these sub-inputs, and use them to prove the conjectures they care about. So specifically, this is a bit unfortunately rendered. This is a super complicated graph, actually. And our method was able to select certain subgraphs in that graph that then the mathematician could use to prove an impactful conjecture with hypercube decomposition in representation theory. But there is a big question of which GNN to use. If you use any off-the-shelf expressive GNNs, we actually did not get very useful signal. So the best results we got were driven by an algorithmically aligned GNN. What happened is the mathematician told us about some existing algorithms that would compute what we care about if we had privileged information that the math theory wasn't allowed to use, right? And then we aligned our GNN to this algorithm. Like we aligned the individual parts of the GNN to line up with what this algorithm here is doing. You can see it looks very much like a GNN, what it's doing here, right? And this is what helped us actually find meaningful sub-inputs that then the mathematicians could use for their research. And what's a more general point to be made here? If there is a target algorithm, but it's inapplicable because it requires some inputs you don't have access to, you could have a more general GNN that is aligned with what that algorithm would do, right? So you kind of reap some prior benefits from that algorithm without needing to run the algorithm. So that's the first one. The second one, yes?
So what do you use as the embedding value if you don't have the privileged information? I guess you gave the privileged information as one of the features.
So you don't give that privileged information. That's the trick, right? So the algorithm would work like this in a low-dimensional space if it had the privileged inputs, right? What we did is we just fed some standard graph structural features like Laplacian eigenvectors and stuff like that, and then encode, process, decode, like we talked about. But the processor is kind of primed to follow what the algorithm would be doing in a high-dimensional space, if that makes sense. Yeah. OK, so the second one, and this might be maybe of a bit more interest to this.
I'm sorry, it is very fascinating. So
yeah.
This means that still you need to have the intuition on what you're looking for.
Yes.
I mean, the alignment is based on the fact that, I mean, for classical algorithm, you know you want to do a shortest path.
Yes.
But for something like this, so it's actually, you know what you want to achieve. You align the neural network to actually crunch the data in order to give you this subset that is in.
Yes. Yes. So in this case, the conjecture was you could do this algorithm even without access to privileged data. And so the mathematician knew exactly what to tell us. But it's great that you ask this, because down the line, we're going to talk about what to do when you don't know what the algorithm is. So that's going to be also quite interesting. Yes?
What's the label when you train the GNN?
So in this particular case, you're taking some features that relate to the group theoretic properties of these graphs, and you output coefficients of a polynomial. So it's a graph-level classification, because the polynomials are integer valued, so you can just predict integers. It's a classification problem. Yeah. OK, so the second one, which I think will be more interesting to this particular audience, is that if you have well-built algorithmically aligned models, they could be very fast heuristics if you want to do combinatorial optimization in practice. This is a work I did with several collaborators from ETH that was published at NeurIPS just a few months ago. So specifically, we look at the task of configuring computer networks. Now, I'm not myself a computer networking expert. I've done a course on it in undergrad, but I know it involves a lot of complicated combinatorial things to solve. Specifically, you might want to produce a certain configuration of the routers in your network to respect a certain collection of specifications, and such that when you then run a particular graph protocol over that network, it results in a plane that respects your constraints. Okay? And the state-of-the-art way to obtain these configurations from these specifications is exact configuration synthesis, which is NP hard and typically requires slow SMT solvers, right? So what we do in our work to try to speed it up is rather than going down this route, is we actually learn the inverse of the protocol using neural algorithmic reasoning, and then use that to go straight from specifications to configurations, sidestepping this part altogether. So let's see how accurately we can do that. We obviously, to be able to go this way, we need a data set from specifications to network configurations. So what we did is we just sample a bunch of random network topologies and configurations, and then we run the algorithm itself, the network simulation algorithm, to get the resulting forwarding plane from which we get the specifications of that plane. So now we suddenly have a data set from specification to configuration, right? We've inverted those arrows. And now let's see if a GNN can learn how to do this, to execute this algorithmic data set. So we have our input fact base, so we have some certain specifications that were extracted from these synthetic models. What we do is we randomly mask some parts of it. So some specific configuration parameters, we set them as question marks. This then gets translated as a graph structure data set where you have a question mark masked feature on a particular node. And now you ask your GNN to fill the gaps, right? So predict the missing parts of this configuration by basically inverting the protocol, right? So this is what we're trying to do. So, and then now suddenly you have a framework that can take you from, your input facts and any constraints you might want to satisfy to like filling the gaps and predicting the parameters that are missing. And it turned out that obviously because we did this in a very kind of forward past GNN manner, it is super fast. So in certain kinds of data sets that are of real world relevance, we have been able to achieve up to 490 times improvement in speed compared to the SMT solver. So much faster, yes?
Sorry, the structure of the graph is fixed in the previous picture?
Yes, so you decide the structure of the graph based on your configuration specification.
So that part is done.
But I thought that's what you're looking for, right? So you're given specifications, you have to figure out the configuration, and part of the configuration is the graph itself, deciding the edges of your route and network.
So it decides the features, right? That's the thing it decides. So certain connection strengths and stuff like that, yes. So basically the specifier wants certain parameters to be filled in, and they will add some parts with questions, and then the GNN will try to fill those in. That's basically how we set it up. So this fact base is both the things that are true about your specification and the things you want decided. So that's the second part.
And what fraction were masked?
That depends on the human designer, right? So in this particular case, I don't remember the exact parameters of the data set, but we had a very kind of diverse, randomly masked data set that we trained on. And it was then deployed on data sets that were of actual importance to computer networking practitioners. So 490 times faster than the SMT solver, yet it still satisfies about 90% or more of the constraints. So obviously it's not perfect, as we discussed before, especially in question that Elias asked. But it's still a good level of consistency for some human-in-the-loop use. And this is especially because even if you use the SMT solver, these input specifications are human-written, and very often they might be unsatisfiable to begin with anyway. So there's naturally going to be some level of iterating, right? So we believe, and one of our co-authors is a networking expert, so they are also supporting this claim, that with this level of precision and speed, this will allow the human network designers to iterate way more quickly. So more generally, in this case, we have a target algorithm, but it's super inefficient. It's an SMT solver algorithm. And we approximate it using a fast heuristic, but in such a way that it's fast and reasonably accurate, so that then if you put a human corrector in the middle of the loop, you might be able to iterate much faster than if you use the original thing. Yes?
Did you model the SMT algorithm really, or the problem domain?
In this case, only the problem domain. So we sidestepped the kind of SMT part altogether. Although, of course, all the configurations were like extracted from what happens after you run the protocol. So it is one possible configuration that could have went into an SMT solver. Yeah, not necessarily the most useful one, but yeah. Okay, so these were just two quick examples, and relating also to what. Yes, Andrea.
Sorry. So. This second application, however, is not very different from what machine learning has been used, for example, in combinatorial optimization in general, right? I mean, there are tasks that, starting from learning from approximating the strong branching coefficients in a certain sense. So the point is, you lose machine learning to accelerate a process that otherwise will take too long in an entire complex algorithm. But this is specific. So in this particular case, you are targeting a specific algorithm for doing this. So the novelty is that one.
Yes. Yes, yes. So this is still, as you said, it's all domains where we know what the algorithm is, and we're kind of using either domain knowledge from a top mathematician or from a computer networking expert to kind of help us set this up. But once again...
The first one is actually more novel in that sense. So the second one is more really on accelerating the process.
Yes, exactly, exactly. So we're in no way the first one to accelerate the process. We just showed it's possible with these kinds of approaches.
For the first one, is it? The output is more like a way to explore the solution for a mathematician to look at, this direction or this other direction.
Yeah, yeah. I mean, I would say so. It's kind of not really a precision microscope. It's like a novelty microscope. Like it hunts for interesting tiny parts of your input so that you don't have to stare at 1,000 nodes. You can just stare at 10. And then maybe you'll see something you like there. Yeah, exactly. Okay, so now let's try to think maybe a little bit more, because both of these examples were like, yes, there is a specific procedure I might like to automate or invert or allow me to explore it. But let's think about more generally, if I build a model that knows how to do an algorithm, could I then use it anywhere else other than in the domain where that algorithm was designed? And to kind of support thinking towards this, I'll prime you with a simple example. Find me the optimal path from A to B. Now, the computer scientists in the audience will likely read this question, and at least myself, I did an undergrad in computer science. I would do this in a very singular way, always exactly the same. I will assume you're asking me to compute a shortest path in a weighted graph, and therefore I will implement Dijkstra's algorithm and run it on the weighted graph that I have, right? So this is the theoretical computer scientist diligently uses their Dijkstra hammers, right? But actually there's a lot of subtleties about what this question is asking that this approach completely ignores, right? Like, why are algorithms built in the first place? They're built to solve real-world problems. And I have seen this firsthand when we built the GNN into Google Maps to predict travel times. It's a much more complicated setting than just find the shortest path. What is even the graph? What are the weights of this graph? The graph is dynamically changing. You have roadblocks, changing weather, traffic lights, all these sorts of things, right? And not to mention the fact that if it's rush hour and everybody's going back home from work, if you let every agent go greedily on the shortest path, you're going to clog the main routes in your network, right? So it's a more global, complicated network optimization. I'm not even talking about the instances of you need to minimize pollution or something like that, which gets even more complicated, right? So you might want to suggest some people to take their bikes rather than use their cars. Right? So the real world problem is far more complicated than what this approach might actually assume. And there's a good reason why this is so abstractified, because when things get abstractified this much, we can prove interesting things about the answer, right? We can verify correctness, we can say how quickly it will terminate and stuff like that. But there is a bridge to cross, and historically that bridge was crossed mostly by humans. So either manually inspecting the problem and figuring out the graphs, or we're writing some heuristics that look at the data and try to predict the graphs. But can we ever hope in the general case to manually do this? I would argue since the 1950s, we've already known the answer is no. And this is a very nice paper that introduced the max flow problem many, many years ago. And at the very start of that paper, they have this very nice paragraph, which basically says that here they looked at studying capacity properties of railway networks. And they said basically, even if someone is closely associated with the territory where these railway networks are, the final answer, like which capacities to put in a flow network, is something that's largely of judgment and experience, and it's basically an art more than a science. So like even if you're very intimately related to the problem you're solving, manually doing this is likely going to lead to a drop of information. So the core problem here is that there is a divide between classical algorithms and the real-world tasks they were designed to solve in most cases, especially as they get high-dimensional. And if you want to satisfy the strict preconditions to run the algorithm, you might end up losing information. So it doesn't matter that your algorithm is provably correct if you're executing it on the wrong inputs. It's as simple as that, right? There's no more or less to say about this. And it's tricky even without situations where you don't see all the data you need to run the algorithm or anything like that. So that's what we tried to, that's what we're really trying to do. And I'll show you how to attack this core problem by what we call neuralizing an algorithm. It's one possible way. We've seen it works reasonably well, and it lines up with all the things I've told you before. So how can we take a target algorithm and neuralize it? This is the question. So as I hope you agree, the problem here is that we have manual feature engineering going from the complexities of the real world to something where the algorithm is applicable. And if the history of deep learning is to teach us anything, this is the kind of thing that deep learning was made popular by in the first place, right? ImageNet, replacing manual feature extraction on images with a deep neural network. So let's replace the human feature extractor with a deep neural network and run the algorithm. We've seen many instances of this in the workshop already. It's a very popular and useful approach. And nowadays, there used to be some problems due to this algorithm being discrete, but there are many established ways now to backpropagate through the solver, including, for example, the work of Marin Vlastelica, which was already cited several times during this workshop. So this is a nice approach, but I will argue that there are certain settings in which it might not be the best approach. So in my opinion, the main thing that in terms of generality might be problematic with this pipeline is that it strongly commits to using the algorithm. Once you compute your abstract inputs here, which are usually scalar level inputs, you're fully trusting whatever comes out of the algorithm, and you don't really have a way to revert your mistakes. So this is what we call the algorithmic bottleneck problem, and we've demonstrated it in several areas, where if you don't have sufficient training data to properly train this part, you're not going to have good enough inputs for the algorithm, so garbage in, garbage out, right? Or even more generally, what if, say in this Google Maps scenario, you don't just want to run a pathfinding algorithm, but you want to run multiple algorithms and kind of integrate them together? Once again, this is a strongly committing pathway. You have no option to fit any residual things that don't come from the algorithm, at least not very easily. So what we try to do in our work is to break this bottleneck for these more general problems and replace the algorithm itself with a high-dimensional neural network. Because where does this bottleneck come from? From these abstract inputs typically being small in scale, right? So we keep everything high-dimensional, and we replace the algorithm with a neural network that maps high-dimensional latents to high-dimensional latents, such that you can then decode the outputs you care about with another neural network. So to break our bottleneck, we replace the hard-coded algorithm with a processor network P. And this now, if you are able to do it right, it fixes a lot of the problems we had. It's fully differentiable, there are no bottlenecks, everything is high-dimensional, and you can fit any residual algorithms that P doesn't explain by just adding a skip connection. It's as easy as that. So, of course, it all assumes I have a good algorithmically aligned piece, so now you might ask, where do we get algorithmically aligned piece from? But I've already showed you this, right? So this pipeline from before, you have a particular algorithm you might want to embed in a high-dimensional space. You can train a model like this, which now gives you a high-dimensional to high-dimensional processor network, which you can then pluck out and reuse for any real-world problem that you want. So now you have your real-world problem with complicated inputs. You take an encoder to a high-dimensional space where you can run this processor and decode the outputs you care about. So this way, you're running the algorithm over the raw data directly without ever needing to do this manual conversion from X to X bar. That is the essence of what we propose. That's the neural algorithmic reasoning blueprint. Yes?
You have no guarantee it will be connected.
Exactly. You have no guarantee it will be connected. But you still get a representational advantage, which means it's useful. So that's basically, although it will be very nice to find ways to bring guarantees into this pipeline. So I'm not saying it's a useless line of research. We should do it. We cannot right now. Yeah. Question?
I mean, I understand the second reasoning that you had about amalgamation of a bunch of algorithms that otherwise are distinct algorithms. But then if the data is low, right, then you still need that for this as well. It's not just unique for the other predict and then optimize route, right?
Yeah. No, that is true. But for example, to give you a kind of a heads up, one environment where we showed this works well is reinforcement learning, where you're kind of learning as doing, right? So if you put an algorithm in there, that actually performs worse than the baseline model without the algorithm, because the algorithm is straying you, on a worse path than where you should be going without correct inputs. Whereas here we have your usual model-free solver, we add the algorithmic component, skip connect, right? And now you can kind of use the model-free part to find a good solution first, and then kind of let your algorithmic part catch up, right? So there is a benefit in doing this, for example, in reinforcement learning in this way. Yeah?
So it would seem to me that for the idea to kick in fully, you need the abstract outputs to be coming from some oracle, which is actually not the output of an abstract algorithm operating on an abstract input. And in our survey, we have this example of the Amazon last mile routing challenge, where Amazon actually doesn't know why the driver picks the route they pick, despite the Amazon algorithm recommending another route. And the reason is tacit information. So the drivers on the street, they see a roadblock, they go differently. That information is actually not really captured anywhere. Yeah. It's not even in the natural input, right?
Yeah.
So it would seem to me that if there exists a correct abstract output, which could be obtained by a classical algorithm, then it's, the operation research perspective would be to say, maybe your model is way too abstract. Let me come up with a slightly more sophisticated optimization model, which maybe has uncertainty, has additional constraints, nonlinear, whatever, and I can model the real problem better, right?
Yeah.
But if the solution is somehow implicit and we don't know of a mapping, then this becomes kind of absolutely necessary in some sense. Like there is no competitor.
Yes, yes. Or if you want to make these solvers more available generally, like, so for example, if someone gives you constraints in natural language, not everybody is an expert to convert these constraints into something a constraint solver would accept, right? So this would allow you to kind of capture what that solver is doing and like allow people to, say, use a chatbot or something rather than, learn operations research, if that makes sense. So yeah, there's many possible ways, but the example you highlight is exactly one that I would be thinking of. Yeah. So as we just discussed, you have this GNN that's pre-trained on the algorithm using the top pipeline, and then you take it and deploy it on the natural task. That way, allowing us to run classical algorithms on inputs that were previously, at least directly, considered inaccessible to them. We have 4 proofs of concept where this successfully worked so far, and I'll just quickly give you a rundown through all of them before we dive into the final part of the talk. So the first one, and once again, the slide a bit cuts out the nice colors, but the first success story we had is in reinforcement learning, our NeurIPS spotlight from a few years ago, Xsylvan, and its follow-up Snap, where we take a frame of Atari or something like that, we embed it into a latent space, we learn a transition model to build a graph of imagined neighboring states, and then we run a GNN that was trained to execute a standard RL algorithm like value iteration, and then use the resulting embeddings to get faster and better policies and value functions. So that's the first example we had. The second example, RMR, that we published in the log conference a few months ago, uses the same idea for self-supervised learning. So say we want to simulate the trajectories of bouncing balls in a super high-dimensional image space. In reality, it's just a low-dimensional physics process in the middle. So what you do is you teach a GNN to imitate the physics process over the nodes, and you plug that GNN into an encoder-decoder architecture that looks at the images, right? And this, once again, gives us better prediction of what these trajectories in the image space will look like. And most recently, our iClear spotlight that will be presented in Rwanda in a few months from now, the dual algorithmic reasoning, where we show you can supervise on 2 algorithms at once that are duals of each other, in this case, max flow and min cut, and then use the GNN that was trained to execute those algorithms on a 180,000 times larger mouse brain vessel data set. So it's a data set of brain vessels in the mouse brain, blood vessels in the mouse brain, and you have to predict, are they veins, arteries, capillaries? I don't know much about mouse anatomy, but I do assume that the main purpose of blood vessels is to conduct blood flow. So if you have access to a flow algorithm in there, probably it will help you. And we found that these pre-trained GNNs on 16-node graphs gave a significant representational advantage on this much bigger graph that they never saw at training time, right? So clearly we get a representation advantage when you plug this on top of a state-of-the-art baseline. So this is just a quick sampler of these works. I don't have enough time in this talk to talk about the specifics, but I would like to kind of talk to you about a more general question, which Andrea already raised several times. I think it's a very good question. Where do we get good processors from? This is something that I think is a super important question because, how do we know which algorithm to execute? In all of the previous cases, we had domain knowledge and computer science knowledge. There was someone to tell us what's the algorithm we care about, and there was some computer scientist who could build a data set that was necessary for this. So how do we reduce the barrier of entry? How do we make non-computer scientists be able to do these kinds of ideas? And how do we build a good collection of processors without requiring prior domain knowledge? For inspiration, we looked at the CLRS textbook, which is, I guess, the standard textbook on algorithms in an undergraduate level. It covers basically everything that most software engineers need in their day-to-day careers. And we extracted 30 algorithms from this book that cover a wide variety of skills. sorting, searching, pathfinding, convex hull finding, string matching, and so on. So we built the CLRS reasoning benchmark that was published at ICML last year, and we have everything open sourced on the GitHub if you want to build models that fit algorithms on this benchmark. And what's unique about our benchmark is we don't just give you sampled inputs and outputs, but we expose all the intermediate steps and we give it directly available to you, including loss functions, encoders, decoders. So you don't have to worry about anything other than building the processor. Everything else is done for you by the benchmark. So here for insertion sort, I give you the entire trace of insertion sort. You know how the pointers of this list change over time as it's being sorted. So your GNN can learn how to imitate the exact steps of that algorithm, not just go from inputs to outputs. Now, of course, we built this benchmark. It allows you to learn something like one algorithm that you care about, but why stop at one? Why not build one model to learn all 30? And this might address the problem that Andrea raised. If I have a good enough, rich enough basis of algorithms in the same latent space, then maybe through backprop I can learn which algorithm I want to use without anybody ever telling me which one it is. Or even interpolate between them, if that makes sense. So CLRS converts these 30 diverse algorithms in a shared graph representation. And secretly, that's actually why we developed it in the first place, to have a simple library where we can train on multiple algorithms at once. And could we then learn one processor with a single set of weights to execute all 30 of these? So this is what we want, right? One processor network with different tiny encoders and decoders that can sort, pathfind, find convex hulls, you name it, anything we have in the benchmark. So it turns out it's not as easy as just take the 30 algorithms and kind of batch them one at a time and do gradient descent. It's not as easy. When we did this, we got nans all over the place, right? And actually, there were some prior works that I was also involved in at NeurIPS 2021 that showed that you can actually only do this really if the algorithms are highly related, like Prim's algorithm and Dijkstra's algorithm. So we dug a bit more, and we realized the key limitation is if you have some tasks in there that have high instabilities, they cause breakages for all the other ones when the gradients push in a bad direction. So we tried to improve our single task stability first, which led us to a huge amount of improvements. We removed the teacher forcing from the original CLRS baseline. We did very extensive data augmentation in the training. We used soft hint propagation. We used static hint elimination. This is all detailed in our paper if you want to read more about it. We are careful about how we initialize our encoders. This was a big one. If you don't initialize the encoder properly, then you're going to have a really bad time. We randomized positional embeddings to make sure the algorithm doesn't overfit to the indexes of the arrays. This was a really big one. Whenever the output is a permutation, like in a sorting task, we actually now use a sinkhorn operator to force the output to be a permutation rather than hope that it doesn't have cycles. And we also have gating mechanisms in the processor to make it more graceful with handling this information. And lastly, many algorithms, especially in CLRS, don't just do reasoning over nodes and edges, but also over triplets of nodes. Like Floyd-Warshall, for example, which does all pairs show the spats. They aggregate information from a pair of nodes with another pair of nodes. So that's 3 nodes at once. So we added an explicit triplet message function in there to compute embeddings over 3 nodes at a time. And some chunking mechanisms to make this all fit in memory at the multitask scale. By doing all of these improvements together, on a single task level, we've been able to improve our previous state-of-the-art baseline by over 20%. Pretty huge improvement. This is all out of distribution, so 4 times bigger graphs at test time. All of these models perform really well in distribution, but out of distribution, they collapse, right? And with all these improvements, yes?
Quick one. Do you tell it what you want it to do, or does it guess what it should do from the input?
So it has the stepwise supervision, so it follows the individual step.
But at this time, right? If you want the shortest path or a convex hull, do you need to tell the processor what to do, or does it guess from the input?
It has to guess from the input. We give it the right encoder and decoder for that task, actually.
Okay.
So
it knows what task it should do.
It has enough information to figure that out, let's say. Yeah. So when you do the multitask training like this, we actually get a mixed bag of results. Like on some algorithms, the multitask in orange is much better than the single task expert. On some, it is worse. But when you take the average, we now have one multitask generalist, which roughly matches the level of performance of single task specialists. And now it gets quite exciting. We also did a very detailed ablation study to show that as you gradually remove all of those improvements that we did, the performance indeed goes down. So it's not just a bunch of random improvements thrown together. They're actually all important for reaching the final level of performance. So we published our generalist neural algorithmic learner as a log spotlight a few months ago. And so have we been successful in now achieving our generalist architecture? Let's ask Reddit. I went on r/singularity, which is obviously a great place to ask about what the potential of some technology is. And yeah, they seem to say this is an awesome technique which has a lot more success in algorithmic tasks. It's a pretty big deal because it's close to one of our guesses how a brain works, apparently. And remember how GPT-3 impresses us with fluent writing but makes blunders in arithmetic, basic logic, and multi-step reasoning? This could be one way to incorporate reasoning into neural networks to reduce such blunders. And lastly, my favorite, if you think of artificial general intelligence as a vehicle, Gato, the DeepMind model, could be a front seat, and maybe our research could act as the side mirrors. They're all necessary for the final car, but some are arguably more important than others. So there's obviously a lot more stuff that I could say about algorithmic reasoning that I had time limits in this talk, I couldn't cover them. So if you want to learn more and to get a detailed list of references, we have a log tutorial that's 3 hours long that talks about all of these things and even guides you through a Colab example if you want to learn how to code some of these things yourself. If you want to know more coming from the combinatorial optimization side, we have this survey that I published together with Christopher, Andrea, Elias, Didier, and Quentin, which is 58 pages long and looks at many ways, not just algorithmic reasoning, that you can use GNNs in combinatorial optimization. Specifically, section 3.3 talks about a lot of the things I told you about today. And lastly, to summarize, we started from something like a curious, inconsequential question that a competitive programming student would ask, but not necessarily a researcher. And we ended up at something that might help us automatically select which algorithm to use in a generally intelligent architecture. So no matter what your stance on the topic, I would argue algorithmic reasoning is likely a technique that in some shape or form will be here to stay. And if you want to chat about it, its implications to AGI or otherwise, please reach out. I have my contact details here. Also happy to chat after the talk. I realized I've done all these papers with a lot more people that can fit on a particular slide. So thank you to all of them. It takes a village. I wouldn't be able to do any of what I told you about today without all these people. Thank you very much.